Hello. So in the class, we were discussing about constrained motion. Yes or no? The topic that we were discussing that was your constrained motion. Constrained motion. In the constrained motion, we saw a string constant. Yes. Now here we are going to take few examples of a string constant. Then we will start with surface constraint. Okay. And after that, uh, pseudo force, and this chapter will be over. So if you look here, example on string constant. Example on string constant. So you can see this is an object. There is a block of mass m. This is another block of mass m. This is fixed. If it is going up with 10 meter per second square, so this has to fall down with the same acceleration that we have seen here, 10 meter per second square, using constant relation. We can see say this thing like here this tension, this is T, here also coefficient of tension is T only. Okay. So we have two ways. I can write here summation, that is T vector dot A vector plus T vector dot A2 vector equals to 0. So you can see T vector and A vector both are in the same direction here. So we will say that is T into 10. Here T and A are in opposite directions. We will write minus of TA equals to 0. We will get A equals to 10. That we have already discussed it in the class also. Okay. Using point method also we can solve this problem. We can break this thing into two segments, and then we can mention these points at 1, point 2, point 3, and point 4. Like this way we can name these points. So we have two segments, 1, 2, 3, 4. And now if you start to look here, you will find that it is going up with 10 meter per second square. This is 0, this is 0, and I'm assuming it is going in this direction. So if I write it here, we will write here minus of 10 plus 0 plus 0 plus A equals to 0. We get A equals to 10 meter per second square. That we have already discussed it. Then the next problem related to based on this, if you just look here, suppose I say that this is one object, and then this is connected to the pulley like this way, and other object is here on this surface, and it is saying that it is going in this direction with some acceleration A. Let's say this is theta. So what will be its acceleration B? We have to find the relation between the acceleration. So if I try to answer this problem using this tension approach, then what you will say? You will say that sir, tension is T here and it is moving in the direction of tension. I will write TB. But here if you look, this is the tension T which is not along the line of motion. This is the line of motion. So we have to look for the tension which is along the line of the motion. And here along the line of the motion is basically the component is T cos theta. So I will be writing here TB minus T cos theta times A equals to 0. And then because same string, so tension will be same here. So I can write here as B equals to A cos theta. That is the one way. Or if you go by point method if you follow, then in case of a point method you will say, sir, this is the one segment of the string, this is the other segment of the string, this is going up with acceleration B, this is 0, this is 0, it is going in this direction with acceleration A. Now recall, I told you that we have to take the component of velocity and acceleration along the length of the string so that the length of the string remains same. So here if I just name these points 1, 2, 3, and 4, you will be writing here minus of B plus 0 plus 0 plus A cos theta, that will be equals to 0, and you will get here B equals to A cos theta. Similar concepts, multiple problems. Look here, suppose if I look for the other problems here, suppose this is the one block, there is another block like this way, and then uh, it is said that it is kept on this surface. Okay, 1 minute. Hello. Sir. 'Hello.' Now look here, if we look for this problem, this is the surface over which the object is moving basically. Now, what is the difference between this problem and this problem? You can see this is moving along this line, which is not along the string, but here it is moving along this string. So, suppose if I say that, let's say it falls down with B oscillation, it goes up with A oscillation. What is the relation between them? And it's very simple here. Its tension is T. You can see here tension is T. You can see, and you can write that's a T into B, because tension and oscillation are opposite direction. Tension and oscillation are in the same direction, equals to 0. You will get A equals to B. This is the one way. Or by point method, if you are solving this problem by point method. So in case of point method, you can write here as this is one portion, this is another portion. Okay, this is 0, it is coming down with oscillation B, and this is 0 and it is going up with oscillation of A. 0 because it is attached to the pulley. We will write minus of plus of B plus 0 plus 0 minus of A equals to 0. We will get B equals to what? That is A. We will get B equals to A here. Okay. So these are some problems where we have to apply the point method concepts. Okay, everyone. Note it down first. Okay, so this is regarding the constraint relation. We will do few more questions on it. Now look here. Suppose this is an object here. Like this way, there is another object that is attached here, and this angle is theta. This angle is also theta. Let's say it is pulled down with speed u. It is also pulled down with speed u. What speed it goes up? So you simply have to draw the body and the tension that is acting here, T and U in this direction. On this, if you see the tension T and T, you will say that, sir, this will be 2T cos theta, T cos theta plus T cos theta. So this is going to become here 2T cos theta in this direction, and then its speed is, let's say, V. Here this is U and here tension is T. So we can directly write here that minus of Tu because they are in opposite direction plus 2t cos theta V minus of Tu equals to 0. And you will get here U minus U plus V cos theta minus U equals to 0. We will get V cos theta equals to 2U. So 2V cos theta equals to 2U. So we will get V equals to U by cos theta. This is by tension method. By tension method. And if we try to solve the same problem using string constant by point method, so by point method, what I will write, I will draw the strings whichever are there, string segments like this way, and I will show all the positions of the velocity. 1, this is 0, this is 0. It is moving up with v. Remember, this angle is theta. Moving up with v, this angle is theta. This is 0, this is 0, and this is u. Now if I start from here, I will write plus u plus 0 plus 0 minus v cos theta minus v cos theta plus 0 plus u equals to 0. 2u equals to 2v cos theta. So we get u equals to v cos theta. So we get u by cos theta. Okay, note it down. Now we have surface constraint. In surface constraint, always remember when two bodies are moving in such a way that they are making always a contact surface. There is a contact surface between the two bodies which are moving. Then the relative velocity and relative acceleration perpendicular to the contact surface will be 0. So note it down. In case of surface constraint, in case of surface constraint, relative velocity as well as relative acceleration perpendicular to the contact surface, perpendicular to the surface in contact must be 0. Or we can say that velocity, acceleration, displacement, velocity, acceleration of the objects in contact along the normal to the surface must be same. Okay. Now look here. This is the surface here. We have one object and this is another object. So this is the surface in contact. And this is the normal to the surface. So if it is moving with speed v2 and this is moving with speed v1, then I will say that v2 must be equals to how much? v1. In that case only the object will be making contact. If v2 becomes greater than v1, then it will separate from the initial block, the first this block. And if v1 is greater than v2, then again in that case it will be moving. It is not possible because if some this object is in front of it and this is here, if its speed is greater than this one, so practically this is not possible. Either they will move together or this will separate. So for surface in contact, the relative velocities, relative acceleration perpendicular to the contact surface must be how much? 0. That is v2 minus v1. That is 0 here. This is your relative velocity. For example, suppose I say that this is a object and there is another object that is kept here. If I am saying this is moving in this direction with 10 meter per second, what will be its velocity? So its answer is very simple. that V must be equals to how much? 10 meter per second. The simple problem. First you note it down, then I will give you more complicated problem on this. So here you will find that we have object A which can move on the horizontal surface, and this is the other one which can slide down, or I don't know exactly in which direction it will go. We have to decide. This acceleration is given. They're asking for this acceleration. How to get the acceleration of this block? So definitely that we are going to use the constant relation here, surface constant. And how we are going to use this surface constant, that is very, very important. So at first I want you to try this question. Trying means decide in which direction this will move, and then where you will focus, on which part of the system you will focus to get the acceleration of this block B. So just give it a try, see whether you are capable of doing it or not. Then I will help you. First, give it a small try. Okay. Now, if you see on this block, first of all, try to analyze the motion of this wedge. This wedge has two surfaces which are in constraint. One is this surface 1. This surface is not moving. So velocity of wedge perpendicular to the surface is 0. This wedge will not move perpendicular to the surface here. It will always move parallel to the surface. This is the first thing. When we apply the constant relation at the first surface, we get this idea. This waves that you see here, this is in contact with this surface. Because this surface is not moving, so velocity of waves perpendicular to the surface is 0. It will always move along the surface. Now, another surface constant is this one. This is the surface 2. So, because it is moving in this direction with 20 meter per second square, so perpendicular to this surface, if you just see, this is 60 degree, this is 30. So in this direction you have a speed acceleration 10 root 3 meter per second square. And in this direction this is 10 meter per second square. Now for B, if I draw for B, then for B this is the one surface, surface 3. This surface is stationary. So block must move along this surface. Surface is stationary, so block must move along this surface. Block must move along the surface. So B must have an acceleration in downward direction, that is, let's say A. This is another surface. This surface is moving. So the component of acceleration along this surface must be equals to 10 root 3. We know this angle is 60. This angle is 60. So I will say A cos 60, this must be equals to 10 root 3. Means this is the direction along which the velocities, the acceleration of both the bodies in contact must be same. So if I apply surface constant here, applying surface constant, what we can write? We can write here that 20 cos 30, this must be equals to A cos 60. That is 20 root 3 by 2, that is equals to A 1 by 2. And we get the value over here, and this A will come out to be 20 root 3. That means this is falling down with 20 root 3 meter per second square. So this is how you have to approach this problem. Note it down. Okay, now try another problem which I'm giving you. A similar problem. It is coming down with 5 meter per second square. This angle is 37 degree, or let's say 30 degree, and this is 10 meter per second square ship falling down. So what is the acceleration of this one? Try to answer it. Okay, now you can pay attention here. So again, I will say that this is the surface where we need to apply the constraint, because this is the common contact between the two moving objects. So along this line, their acceleration, their velocities must be equal. So this angle is 30, I can say this angle is also 30 here. And then we can also talk about this one. If this angle is 30, what will be this angle? This angle will become 60 degree, because if I just drop a perpendicular like this way, then you can say, if I draw another line like this manner, so you can see this line and this line are parallel. So this angle will be 30 degree, and because this is perpendicular, so this angle will be 60 degree. So this angle will be how much? This angle will be 30 degree, and this is 10. So I will write here, along this line, this is the line along which we have to apply the constant. Along this line, 10 cos 30 must be equals to a sin 30. We will get 10 cos 30 root 3 by 2, that is equals to a by 2. We will get here a equals to 10 root 3. This will be the answer to our given problem. Now this is a combined concept of string constant and wedge constant. Here it is said that if it is moving in this direction with a acceleration, or let's say a acceleration, find the acceleration of block B. They're asking us to calculate the acceleration of block B. Calculate the acceleration of block B. Okay, so now if we pay attention to this problem, you can see that we have a surface constant here, and this is very logical to say that when it is moving in this direction with a, it is falling down with some acceleration, let's say that is b, but b will always have to maintain contact with a, so b will also have one acceleration in this direction, same as that of a, because a will keep on pushing it, the b will be falling down, along with it will be also going in this direction. This is very logical, okay? And even if we apply the constraint here, we can say, like if I apply constraint at this surface, so at this surface it has, a has acceleration of a, and b will have acceleration a dash. So these accelerations must be equal if they have to maintain contact. So I can say that the b will have one acceleration in this direction, and this acceleration b is in this direction. For this b, we can use the string constant here. You can see this is the one part, another part, another part. Total three parts of the strings are there. So this is 1, 2, and 3. This part is not important because it is not changing its length. Now you can see this part is attached to the pulley, and the pulley is going in this direction because it is on the block A. So this will have an acceleration A in this direction. This will also have acceleration A in this direction. This point will also have acceleration A in this direction. This is falling down with B. This is a stationary, this is stationary, this is moving in this direction with A because it is attached to the block A. If I start from here, then I will be saying that 1, 2, 3, 4, 5, 6. I will say minus of a plus 0, here also plus 0, here also minus a. You can see this is 90-degree, component of a along the string will be 0, component of a along the string will be here also 0. So 0 plus 0 plus b equals to 0. We will get here b equals to 2a. So we will get acceleration of block B, acceleration of block B, this is going to be what? Acceleration of block B will be in this direction, that is 2a. In this direction, this will be a. So a resultant will be how much? A resultant will be under root of 2a of a square plus a of a square, that is root of 5a. This will be the acceleration of this block B. So these are the some important concepts, okay, that we have finished now. One more topic is left that we will finish it in the regular session, okay, and then this topic will be over. And after that, we can start matter heat transfer, which is coming in your exam. Okay, everyone. All right then. This much is for today. After noting down, you may leave the sessions.